Let's look at an example of linear regression. So in this problem, it's looking for a relationship between cans of beer and the blood alcohol content in grams per deciliter. And in this, it gives me the summary data here with intercept, an estimate for the intercept, a standard error for the estimate, a t-value, and some sort of a p-value, some sort of a probability. And it does the same thing for something that it labels as beers here. And this can be a little bit hard to understand what's going on in this table, so I'm actually going to rewrite this with the parts that I think are probably the most important. And those parts would be the y-intercept, and much more important than the y-intercept is the slope, because the slope is going to tell me something about the nature of the relationship between the variables. And in this problem, it gives me an estimate for these things. And intercept is going to be my y-intercept. So a guess for what my y-intercept should be is negative 0.0127. An estimate for what the slope should be is a positive 0.0180. The standard errors tell me how those things vary. And I could use those to make confidence intervals for the slope or y-intercept, but those t-values or t-scores are going to be ultimately what I need to do a test for linearity, to see if this is a model that I would want to use to make predictions. And those probabilities, I'm going to label those as p-values. I had 0.3320, and I had 0.0000. We would call that 0 plus. Now, looking at this graph, I'm noticing, and I'll see if I can draw a line in here to the best of my ability. Okay, there's my line. And this looks like it is a moderately strong fit here. Not amazing, but there's definitely looks like there is a positive relationship between these variables. In particular, the more cans of beer that are consumed, the blood alcohol content seems to go up. And it's to the point where I can almost make some pretty nice predictions. At least I could if I had the equation. Then I could predict, if I've had 7 cans of beer, what my blood alcohol content should be. So using this, I could make a prediction about like how many cans of beers I could safely consume before hitting a certain blood alcohol content level. So I would describe the relationship between the number of cans of beer and the blood alcohol content here as a moderately strong and positive relationship. The table is actually giving me the equation for what this should be. My line of prediction, my y hat line, is going to be mx plus b. The estimate for the slope is 0.0180. The estimate for my y-intercept is negative 0.0127. Plus a negative is the same thing as subtracting. So I have a line of best fit. I have a linear regression line. I have a least square line of y hat is equal to 0.0180x minus 0.0127. I can plug in 7 beers. It will tell me my estimate here. I could plug in 5 and it would give me an estimate. I now have some sort of equation that will go from number of beers to a guess for what that blood alcohol content should be. On its own already, pretty useful. Now, let me clear up that screen. And let's look at some of the other parts to this, though. write the equation of the regression line. So I should have mx plus b, but I'm noticing that the x is here. The slope always goes by the x. So they're trying to trick me up by putting the x second, but I'm not going to get tricked. The slope is always next to the x. So that's the y-intercept first. And that gives me my equation. It asks me to interpret the slope. And slope is your change in your y value over the change in your x value. It's rise over run. So if I have a slope of 0.0180, and if I want to make that a fraction, you can make anything a fraction by putting it over 1. I can figure out what this represents by taking the units for y and the units for x. The units for y here was blood alcohol content. And this was in grams per deciliter. And on the bottom, my x values were cans of beer. And what this slope tells me, and I think this is really interesting, is that for every additional can of beer, my blood alcohol content would go up by 0.0180 grams per deciliter. So this gives me a really specific relationship between these two variables. So for every additional can of beer, the blood alcohol is expected to increase by about 0.018. Now, just because I have this relationship, it doesn't mean that I should use it. I want to make sure that I have evidence, strong evidence of a linear relationship between my variables. And ultimately, the thing I am more interested in, besides where the line starts, is how steep that line is. So when I'm doing a test for linearity, I'm always going to have the same null and alternative hypothesis. The null hypothesis is going to be that beta, this is representing that slope, it's often called my beta 1, is equal to 0. And this would mean that there was no slope or no linear relationship. My alternative hypothesis is going to be that the first unknown value that I'm predicting, my slope, is not equal to 0. And this would mean that there is evidence of a linear relationship. Now, I always get a little bit hung up with the 0 meaning no linear relationship and not equal to 0 meaning a linear relationship. No linear relationship, think no meaningful slope. Alternative hypothesis means that there is a slope that matters. In particular, maybe this is a meaningful slope. When I'm looking at this model, it's going to be called a linear regression t-test. The degree of freedom is going to be the number of points minus 2. Now, looking at this problem, it doesn't give me a ton of information. Here we examine data from 16 students. Oh, great. So actually, I do have my degree of freedom. It's 14. If I want my p-value and my t-score, that's going to be related to the slope. I care about the slope. I'm going to make this big. So when I'm looking for the t-score, the slope is the thing that matters. And a t-score of 7.48 is super rare. It has a p-value of 0 plus. So I have my hypotheses, I have my model, and I already have my t-score and p-value. Now it gave me this technology, but I can find this stuff using technology if they don't give me the table. Final step is conclusion. And with the p-value of 0 plus, this is less than any reasonable alpha level that you would want to select, in which case you would reject the null hypothesis, which means we have evidence of a linear relationship. Now, unfortunately, it didn't give me my r or r squared, so it's not telling me how good that linear relationship is, but at least I have evidence that I could use this line. So if I wanted to publish these results, that'd be a reasonable thing to do. So my null hypothesis is associated with an increase. Ooh, tricky. They're looking for an increase. That's okay. So we'll check for an increase too. P-value, 0 plus, so 0.0000. Since the p-value is less than 5%, we reject the null hypothesis, and there is sufficient evidence to show that there is a significant relationship between blood alcohol content and number of drinks a person consumes. The correlation coefficient for the number of cans of beer and blood alcohol content is 0.89. Nice. They gave me my R. My correlation coefficient is my R. And that is 0.89. If I square this, I get R squared, and this will tell me roughly how good of a fit this is. This will be the amount of variation that I know. So if I take this 0.89 and square it, I get 79.21%. That's pretty good. Leave your answer as a decimal. Okay, I will. Round to 3 decimal places and interpret it. So 79.2% of my variation is explained by the number of cans of beer. This is telling me how good that model is. And that's pretty high. Looking at all these parts, pretty good. I have a thing that's 79.21% good for roughly for that fit. That's a really strong fit. I have a p-value of 0 plus. That's a lot of evidence there that this is a linear relationship. I have a specific slope describing that relationship. For each can of beer, my blood alcohol should increase by roughly 0.018, and it gives me my line of best fit. I hope you found this useful here, and as always, ask me questions if you have them.